We are now into the last lap of our 11th standard with this miscellaneous exercise, and miscellaneous exercise we are going to start today, and we are just going to briefly get across with the problems and see what they are saying. In the problem number 1, they say that the box contains 10, this is a part 1 video. A box contains 10 red marbles, 20 blue marbles and 30 green marbles. 5 marbles are drawn from the box. What is the probability that all will be blue and at least one will be green? That's a question. So let's quickly get across with what they are saying. Now anyhow, for any experiment we require the sample space. Then from the sample space we will go to the respective probabilities and get the answer. So it's a box which is containing 10 red balls, 20 blue balls and 30 green balls. In the first event they ask us that the 5 balls that we are drawing, they are all blue. What is the probability? And in the second one they are asking us that at least one of them is green. No, so one can be green, the other one can be lots. So let's before that let's write, let S be the sample space. Let S be the sample space. Yeah, so what will happen? You will have S made up of how many elements? Therefore n of S will be 10 plus 20 plus 30, which is 60 in number. The n of S is going to be 60. Let's check let's define the first event. Let A be the event of getting all blue, of getting all blue balls. No, we shouldn't say that n of S is 60. Why? Because we're drawing 5 balls, right? And if we keep n of S as 60, it means that 60 choose 1. So that will not be correct. So we will call it like this. N of S for this particular experiment is this C5. That means it is 60 C5. That's more correct. Okay, this is the way of doing it. Yeah, so that's how it is coming, 60 C5, because we're choosing 5 balls, right? So in how many ways we can do it? That is how it is. That's how the total. Now A be the event of getting all blue balls. We see here clearly that there are 20 blue balls, right? So in how many ways we can choose these blue balls is from 20 we have to choose a 5. So it can be done in 20 C5 ways. So that's about it, right? So what's the probability of choosing the all blue balls is n of A by n of S, and that's practically 20 C5 and by 60 C5. It's a huge number. Okay, even if we plan to kind of work it out, it is like too laborious. So we can leave it like this. For the first subpart, the answer is 20 C5 by 60 C5. Then we can take this second subpart, and in the second subpart they are asking us at least one green. Let B be the event of getting at least one green. Now you just check at least one green, that if it is one green and 4 non-green, okay, at least. So 2 green, 3 non-green, then 3 green, 5, so 2 non-green, then 4 green and 1 non-green, or all the 5 greens, right? This is at least one means so many possibilities are coming. So you have to find out probability of all these added up. That will be your answer. Now in cases which are so laborious, we have to learn it here also and for the next year also. When cases like this comes, if you can take the complement event, then 1 minus a complement will give you the required answer. So which is the case that's not considered here? No green, right? 0 green and 5 non-green. That's not considered. So if we kind of find the probability of 5 non-green balls and do 1 minus that probability, then you will get the probability of this. So see, actually for this particular thing, so many events are existing, out of which we require all this, only this is not included. So if that only one is not included, you can always do one. That means it's a complement. Okay, it's a complement of this event. This event is B complement. So you just take the probability of B complement, 1 minus probability of B complement will give you the answer. So that's also one technique, and it is an important technique which we generally use even next year in bounty. When instead of doing so much, it's better to do that and get the answer. So that's how we'll be doing even this case, and that's how we'll be getting the answer. So probability of getting at least one green is B, and B dash is the event, of getting no green, right? So how do you list that you're not getting a green? So if you're not getting a green, you have to do this away. So how much you're left with? 10 and 20. Non-green is 10 and 20, same like before. 10 and 20 C5, which is 30 C5. So what is your required probability? Probability of B is 1 minus probability of B dash, which is 1 minus n of B dash by n of S. And that way, I don't want to borrow that place, so I will continue here. 1 minus 30 C5 by 60 C5. You can leave it here, or you can write when we equalize 60 C5 minus 30 C5 by 60 C5. Right? That's the answer. Yes. And depends. If you have all the patience, you can expand and get the answer. That's about it. So that's our problem number 1. Now let's quickly go to the problem number 2. What does it say? 4 cards are drawn from a well-shuffled pack of 52 cards. Find the probability of getting 3 diamonds and 1 spade. Yeah, you have to get 3 diamonds and 1 spade. So specific. Yeah, it's so specifically told that you should get 3 diamonds and you should get 1 spade. Very specific, and so very easy to do this problem. Anyhow, let's start. We are choosing 4 cards out of the 52 cards. Can be done in 52 C4 ways. So that is our sample space. Then in order to get the 3 diamond and 1 spade card, we will define the event and we will try to see how we can get it. So let's start. Let us be the sample space. Okay, therefore n of S is 52 C4, right? And let A be the event of getting 3 diamond and 1 spade, right? So n of A. In how many ways you can do it? Now, how many diamond cards are there? 13 diamond cards. How many spade cards are there? 13 spade cards. So if you want, we can make a small indication like that. So that gives us a choice. There are 13 diamond and 13 spade cards, right? So n of A is from 13 we are choosing 3 diamond cards, and from 13 we are choosing 1 spade card. So you've got n of A like that. When you write P of A, it is n of A by n of S, which is 13 C3 to 13 C1 by 52 C4. And this, as we solve, we will be getting the answer. I'm just getting across. Yeah, again, that's one's own convenience. If we are okay with the solving, we can get across, solve it, get the answer. Otherwise, it's fine if we leave it like this. It also depends upon the mark that it is carrying. Depending upon how the mark is carrying, we will go on to solve this and we will get the answer. Otherwise, it's fine if we leave it like this. So that is about this problem. Then we have the problem number 3. Now problem number 3 says that we have a unique dice. Okay, like always we know that the dice is numbered, the faces of the dice, they've got numbers starting from 1, 2, 3, 4, 5, 6, right? But this dice is not like that. Its 2 faces has got the number 1. Its 3 faces has got the number 2. And its 1 face has got the number 3. Now if this is the case, you should find, with this condition they ask us to determine probability of 2. Probability that you get the number 2 or you get the number 1 or 3, or you get the number not 3, right? So that we will get across. So let S be the sample space, S be the sample space, and therefore the faces of the die has numbers 1, 1, then 2, 2, 2, and 3, right? Now so 6 outcomes only. Okay, anyhow they are different different faces representing the numbers like that. It is 6. Now let A be the event of getting 2. Let A be the event of getting 2 on the die. How many choices do you have for getting 2? 1, 2, 3. 3 choices. So n of A is 3. I'm just checking the question. Yes. Yes. And therefore probability of A will be n of A by n of S, which is 3 by 6, which is half, right? That's about the first thing. Then second thing, we can write like before B be the required event, or we can write let B be the event of getting 1, be the event of getting 1 on the die, and C be the event of getting 3 on the die. How many ways can we get 1? 2. How many ways can we get 3? Only 1. They have asked us 1 or 3. So that means they are asking us probability of B or C. That is probability of B plus probability of C minus probability of B intersection C. Now there is no intersection between this. There is no commonness. You know what one phase gives, what the other phase is going to give. They have got nothing in it. There is nothing like an intersection in case of a die. No, never happens. So therefore they are mutually exclusive events. So that is why the intersection will be 0. So that you can state. Also B and C are mutually exclusive. Therefore n of B intersection C is 0. Like that, when we try to list this n of B by n of S actually. So it is 2 by 6, this is 1 by 6, and this is 0. So this is 3 by 6, which is half. So that is about it. Then we can take the third part where they ask not 3. So 3 have we covered anywhere? Yes. So probability of not 3 we have learned long back that it is 1 minus probability of 3, which is C. So that means it is 1 minus probability of 3 we have learned it is 1 by 6. So when we equalize, it will come to 5 by 6. So probability of not getting C is 5 by 6, and that's how the thing goes on. So that's about this part. With more problems we are coming in the next part. Thank you.